Hello everyone. Welcome to this course of Digital Logic Design. I am your instructor Neeraj Goel and I am an assistant professor in Department of Computer Science, and we'll keep interacting during the course and you can let's try to start this course of Digital Logic Design. Before going into detail, in this particular lecture, we'll try to understand what is the meaning of digital logic design or a digital system. Okay, so digital system is formed with these two words, digital and system. What is digital? Digital means discrete and discontinuous. Discrete means this is certain, like 1, 2, 3, 4. Discontinuous means it's not continuous. Neither it is continuous in space nor it is continuous in time. Space means we can also say continuous in values. So all of you might have heard this, you might have used this phrase as a decimal digits. Because in our decimal representations of number, we call 0, 1, 2, 3, 4 up to 9 as digit. That's called a single digit. Okay, and when we club together multiple of such digits like 23, we have two digits, 2 and 3. This 23 became a number. It is still a digital number because it is still discrete and discontinuous. What do we mean by discrete here? So for example, there is a number 23 and the number 24. So in between these numbers 23 and 24, there is a infinite number of possibilities, infinite number of numbers which could be possible between 23 and 24. You can see 23.1, 23.11, 23.10001. So in such way we can have infinite possibilities between any two numbers, but because a digital number are discrete, so there is no possibility of anything between 22 and 23. Okay, so if we combine multiple such digits, it will become a large number, but it will be still digital in nature. Now this is what is the meaning of digital. What is the meaning of digital system? System is usually a close entity which has some definitive input, some definitive output. Now a digital system will take a digital input, means some discrete numbers as input, and it will also give digital output. Plus it will also process this digital input. It will also process this information as a digital input and will do some sort of calculations and give this output. Because it is taking digital as an input, it is bringing out digital as output, so all the processing inside will also happen using digital logic, or all the intermediate inputs or intermediate signals or intermediate values will also be digital in nature. Okay, so in other words, my digital system will be taking digital input, will be processing digital input, and will be giving digital output. Now let us see, on the other hand, if we see a real world around us. So what we see, let's say we are sitting in a home, we see walls around, we see TV, we see mobile phone, all of these things. So whatever we see, whatever we hear, whatever we speak, that's not discrete, that's all continuous. And continuous not only in terms of values, but also continuous in terms of time. So for example, when we are speaking continuously. So there is a notion of time there. Plus there is a notion of volume, and this volume is also perceived as continuous. So essentially, whatever around us, whatever senses we have, hearing, seeing, or observing, watching. So all of these senses are perceived as continuous, and continuous in space as well as continuous in time, or continuous in terms of values plus continuous in terms of time. So there is one important question that can be raised here, that if we perceive all the world around us as analog, means not digital, as a continuous word, then why are we talking about a digital system? Or in other words, can these digital systems be of any utility? Can there be any advantage of a digital system which is discrete in nature? Okay, so to see this particular question, whether it can be of utilization, whether there is any benefit in with respect to analog, we'll see in some of the later lectures. But let us try to see, can we see example of some digital system around us? Okay, so let's try to think a little bit what example we can think, what example comes to our mind when we see digital information processing. Okay, so because we are defining digital information in form of digits, so probably mathematical calculations looks like the best example of a digital system. So maybe a calculator is an example of digital system, very small digital system although. So but similarly we also understand, because most of you are from computer science background, so you also see all the word of computing, like your computer, your laptop, smartphone, mobile phones, all of these things are also digital in nature. That's what we understand. So we don't know how, but we at least understand that all of these take some sort of a definitive input. So whenever we press a key on a keyboard, then it is a discrete value. It doesn't associate with the time. Okay, so because it's a discrete, so it would be converted somehow in the system, but it would be a digital system. Okay, so these are the good examples which we see around. Can we think of more? So outside computing, outside computer, like computer, laptop, smartphones, they are all equivalent these days. Can we think of something outside? Then we can say probably internet, or the devices associated with the internet. They're all also digital in nature. Yeah, correct. So can we think little bit outside? Can we see in our homes, in our houses, do we see some more digital systems? These days, like most of us would have LED TVs or LCD TVs. Some of us also have smart TVs. They're also a digital system, completely digital system. A smart TV which is governed by internet, okay, which is taking input from internet, which is showing in form of small LEDs. Each LED is a discrete entity. Whatever colors each LED shows, that's also discrete in nature. Okay, so similarly set-top boxes are also digital in nature, which is helping our TV to browse through various channels and give us various information guides or selection of various channels. Similarly, digital cameras. So all of these things are essentially part of our consumer electronics goods, or helping us in making our life smarter. They are all digital in nature. Okay, and it's not only these consumer goods, but also other things which are becoming more and more smart. So for example, automated washing machines, some part there would be a digital, that's why it is being automated. Air conditioners will also have some sort of a control unit, that's why people sell it like a automated system. And the things which we don't perceive as digital, but also in our cars, whenever you use this particular word, power window, power steering, power brake, so most of these components in this car is also digital in nature. So this way we see all around us a lot of things which can be termed as a digital system. Now, if we go back in the history, then we can also see there are 4 industrial revolutions which happened. First one was because of steam engines. That was the original industrial revolution. And then after that, because of birth of electricity, more automation happened. There were birth of you could see in that era electronics computers as well as mechanical computers also. Large scale industrialization happened. But the major push to industrialization happened because of digital revolution starting from early 80s. Okay, so because of invention of something called large scale integrated circuits or integrated circuits, that means lot of these transistors could be packed onto one chip. Now, because of that integration, lot more number of transistors could be pushed into a single chip. This is now called very large scale integration or VLSI. So that's the heart of digital revolution. Because of that, we could see more and more processing systems, and all the digital products what we see around, they are all because of that. And eventually, just because we had computers, internet changed the way we use to see system. And particularly in this crisis of COVID, where we cannot talk to each other face to face, this digital revolution is on the rescue. We can record lecture, you can see it offline. We can have one-to-one correspondence, we can have one-to-one discussion, face-to-face discussion. We can also have one teacher's instructor speaking to thousands or hundreds of students at the same time in online teaching. So all of these things are possible because of digital revolution, because of internet. And all of these things happened because we had this digital system in place. So this also answers one of the important question, which is why we are teaching this course, or why you as a computer science undergrad student is listening to me or is doing this particular course. This particular course is a core course for computer science students, and this is a elective for maths and computing students. So why this is core? Because whatever computer we build, whatever computer programming we do, underneath the hardware which is doing all the processing is a digital system. And it is very important for us to design an efficient system so that we can produce a system which is less in cost, good in performance, less power consuming. And you can see the effect of these 3 keywords, area, performance and power, in the 4th industrial revolution, which would be led by machine learning, artificial intelligence, Internet of Things. So some of you may be knowing that this machine learning is not a new technique. It is a technique which we know from last 50-60 years, but it became prominent now, suddenly prominent. Why? Because of availability of hardware which is fast, which is efficient, availability of lot of storage which can be done. So because now we can do lot of computation in very short span of time, that is why we could deploy such algorithms which require that complexity but can be done in fraction of seconds. So that also emphasizes a requirement to design such a hardware which can do enormous amount of computation, which was probably not possible in past, but would require in future. So with this invention of new machine learning and AI algorithms, we would require our system to be more complex, so more computation have to be done within the same area or within the same cost. On the other hand, the other part of this fourth industrial revolution, Internet of Things, IoT. So this IoT requires all the computation nodes to be as small as possible, as low power consuming as possible. So this low power consumption, this small area, is also another conflicting requirement. So at one end we would require very fast and efficient systems. On the other hand, we also require very small power consuming, very small systems. Okay, so because hardware design, or understanding at least how hardware design works, understanding or designing efficient hardware is the core of computer science. That is why we will study this particular course. And what we'll do in this course, we will try to design digital systems. We'll try to learn how to design a digital system. So for designing digital systems, first thing we have to understand is how to represent any sort of information in form of in digital form. So for example, information could be continuous in space, continuous in time. How we can represent that information in a digital or discrete or a discontinuous form? Still, we do not have any kind of loss in information. So that would be our first module. And after learning how to represent information, then we will learn the basic algebra. This algebra is called Boolean algebra. So along with Boolean algebra will tell us how to process this information. And then to implement that Boolean algebra, we will also learn different kind of logic gates, and how optimization can be done, how the same logic can be represented with smallest number of gates or smallest area. So this would be our second module. After learning Boolean algebra, basic logic gates, then there are two kind of digital systems. One is called combinational logic, another is called sequential logic. So in module 3 we will learn about combinational logic, and after finishing combinational logic, in module 4 we will do sequential logic. So after doing this basic understanding of combinational logic and sequential logic, then we will try to learn or integrate both of these components in some system. So this module 5 would be essentially a number of case studies, number of examples, so that we can design a little complex system using both combinational logic as well as sequential logic. So all the components which we have learned from module 1 to module 4, we'll try to design a full system. So whenever we are talking about design, it is more at conceptual level. But you see, all the digital systems are essentially hardware in nature. So in our last module, we will talk about technology aspects. We'll try to synthesize things onto hardware, and hardware specifically we call here FPGA, field programmable gate array. So there is a prefabricated chip. On this prefabricated chip, we can configure any digital design, whatever we have designed during the course. Okay, so this was the theory part of our course, and this is how we'll flow, this is how our modules will go time to time. Now what about the lab part? In the lab part, what we'll do is we'll try to learn to represent a digital system in a hardware description language like Verilog. This Verilog is C++ like language, but it is more suitable for representing or for describing hardware or describing a digital system. So this Verilog hardware description language, so there are many hardware description languages, but we will choose Verilog among them. Now this hardware description language we'll use for simulation and synthesis. Using simulation, we can see whether the behavior, whatever we would like to model, is coming out same or not. After simulation and synthesis, then we can implement the same design onto an FPGA hardware. Okay, so this third part would require actual FPGA boards. So this may not be possible until we are working from home or we are studying from home. When you people will come back, you will be here in IIT, then we can at least have some demonstration or some time we can spend to do actual FPGA implementation. But so for the time being, the assignments would be mostly describing things in Verilog and then doing simulation, and also sometime doing synthesis to understand how it would be fabricated on FPGA. Okay, so this would be the overall course about, and then let's look at some of the logistics. So what do we expect after doing this course by November, and what should we expect to learn? So first thing I expect you to learn is fundamentals of digital design. So what is fundamental here? Fundamental is algebra, Boolean algebra, basic gates, logic minimization. So these are the fundamental things. Fundamentals about combinational logic, fundamentals about sequential logic. So state machines are the basic fundamentals of sequential logic. So these fundamentals is most important thing we learn, and along with these fundamentals, then the second part which we'll also see is using these fundamentals, designing some kind of a standard logic. So the standard logic could be arithmetic operators, encoder, decoders, multiplexers, counters, registers, many such standard logics we'll try to design using basic logic gates, using combinational style or sequential style. Another thing which I expect that we learn by the end of this course is that given a digital system, we should be able to analyze that what is the cost of digital system, and cost would be represented usually in terms of area, because area is directly proportional to cost of fabrication area, and then what is the delay or latency, what is the time this particular system task will take to complete a particular task. Okay, and there could be other cost matrices like power that we'll try to see how much we can cover, but at least we should be able to analyze delay and area of a system. Okay, now based on first three learned things, then we will try to design a whole system. So this whole or a bigger system is also one of the objective. Like we should be able to break the system into smaller parts and then use our skills of designing combinational logic, sequential logic to design a bigger system. Along with these learning objectives, these 4 learning objectives, during the course we'll also learn how to describe a digital system in a hardware description language like Verilog. There are 4 books which are mentioned here. First one is Fundamental of Logic Design. So this is the primary textbook which we will be following during the course, and all other from the other books like from Maurice Mano or from Kohavi or from Digital System Design using Roth by Roth. So all of them, from the rest of them will take 1 or 2 topics, and I'll mention it explicitly that from which book we are doing a particular topic. All of these 4 books are available online, so you can search on Google and we can get PDF of all 4 of them. If you're not able to get, then you will shoot me an email or ask TA, then they will tell you about the PDF. So with this I will close this particular lecture. So in summary, we have learned about what is a digital system, what is the importance of this course, and what would be different modules in this course. Thank you very much.